Let me finish example 1. Sorry, I got cut off. So we have, we don't have specific rules for cotangent squared x, but we can use trig identities to rewrite our integrand. So 1 plus cotangent squared can be rewritten as cosecant squared x. And once we replace 1 plus cotangent squared x with cosecant squared x, now we have a specific rule for cosecant squared x, which is simply negative cotangent of x plus c. Okay. Example 2, sometimes we may need to rewrite in a different form to match the integral formula. So sine over cosine squared x, we don't have a specific rule with 1 through 6, but maybe if we can write this in a different form to try to match with one of the existing ones. So I can first play around with the order and also split this up into cosine x times cosine of x. And I can treat this sine of cosine, sine over cosine. I know this is tangent. And I also know that 1 over cosine is secant. So tangent secant, we do have a rule for tangent secant if we look above. Secant tangent simply secant of u. So integral of tangent secant will be secant of x. Okay, will be secant of x plus c. Okay. So it may not be very apparent with the rules that you could use. So it does take a little bit of guessing, checking, and rewriting to see if it'll fit one of the rules. Okay. All right, next topic is differential equations. Okay. So differential equations simply are equations that involve derivatives. Okay. So here are the steps that we're going to take to solve these differential equations. We're not going to get too much into it right now. We're just going to solve simple ones, and then we'll talk about the more involved ones in future chapters. So first step is rewrite y prime as dy dx if needed. Okay, the reason why you want to rewrite y prime as dy dx, it helps us see the different portions once we decide, once we have to split them up into groupings. So number 2, we want to separate variables on either side of the equation. So we want the y's and dy's together. We want the x's and dx's together. Okay, third step, we take the integral of both sides using the appropriate rules that's available to us. And then we may need to solve for c if the problem asks you to find specific differential equations. So let's look at example 3. Solve, suppose y prime is equal to 2. Solve for y. Okay. Okay. First thing we can do is we can rewrite y prime in a form that is visually easier to take our next step. So y prime, rewrite as dy over dx equals 2. Next step, separate the variables. So we want the dy on the left side, and let's move any constants on the right side along with the dx. Okay, so there's no other y's that need to go that's available in our differential equation, so we're only going to have the dy by itself on the left. Okay. We take the integral of both sides. Integral of dy is the same thing as integral of 1 dy. Integral of 2 dx, we apply the appropriate rule here. So integral of 1 dy will simply be because the constant of integration, or the independent variable, is y on the left side. So integral of 1 dy will simply be y. Integral of 2 dx will simply be 2x. And then both sides will produce a plus c, but we only need to write a plus c once on the right side of the equation. Okay. All right, let's look at example 4. We're going to solve this general differential equation. So what this means is we don't have to solve for c. We can leave c in the solution. solve for y. We have our differential equation dy over dx equals x cubed. The equation is already y prime is already written in terms of dy dx, so we can skip the first step. Okay, cross multiply, or we can begin to separate the variables. So dy on the left, and then the x cubed dx on the right. Okay, we want the y's on the left side, the x's on the right. Take the integral of both sides. So the integral of 1 dy will simply be y. The integral of x cubed dx, go with your power rule, add 1 to the exponent divided by that new exponent. So x to the 4th over 4 plus c. Okay, example 5, now we're moving into finding a specific differential equation. So we're going to have to solve for c once we get to our indefinite integral, once we solve our general solution. So we have y prime is 3x minus 4, and the point 410 is on the graph y. So eventually we're going to use this to help us solve for c. All right, so we set up our differential equation. Y prime can be rewritten as dy over dx. Okay, let's move the dy dx to the right side. Dy is equal to 3x minus 4 dx. We take the integral of both sides. Integral of dy is equal to integral of 3x minus 4. So the left side will just give us y. The right side, we apply the appropriate integral rule. 3x becomes 3x squared over 2. Negative 4 becomes negative 4x, and then we just need to have plus c once. Right, so now we have a general equation, but we're looking for a specific equation, so we're going to have to find the c value that will provide our specific equation. So we're going to replace x with 4, replace y with 10, so we can actually solve for c. So 10 is equal to 3 times 4 squared over 2 minus 16, 4 times 4 plus c. We solve for c. 10 is equal to 24 minus 16. So we get 8. 10 is equal to 8 plus c. Subtract 2 from both sides. 2 is equal to c. So once we have our c value, we can go back to our general equation and replace c with the constant that we found, which in this case, the specific value that we found, which is 2. So y is equal to 3/2 x squared minus 4x plus 2. All right, example 6. These are more differential equations. Now we are starting with f double prime, and we want to work our way back up to our original function. So we're going to have to find the integral twice. All right.